Good morning, everyone. I'm Kartik Nayak, and today I'm going to present our work on some vulnerabilities are different than others, studying vulnerabilities and attack surfaces in the wild. This is joint work with Tudor Dumitras from University of Maryland and Daniel and Petros from Semantic Research Labs. So in the recent past, data breaches and cyber attacks have been very common. Think of the recent iCloud bug that happened or the iOS vulnerability. Think of the Adobe Reader Media API vulnerability that affected a large number of users since 2009, or the config worm which affected a large number of Windows users since 2008. Each of these cases happened because there was a vulnerability in one of the systems, and all of these companies have been introducing newer security technologies so that these vulnerabilities do not come up. For instance, ASLR or DEP was introduced in Windows Vista, and sandboxing or protected mode was introduced in Adobe Reader 10 or Internet Explorer 7. The question we ask is, can we actually measure the impact of any of these system security techniques? There exist metrics today, for instance, but however, these metrics do not do a good job of actually evaluating. For instance, CVSS score, they do not reflect exploits in the wild. The classical defect prediction metrics, they actually have a low recall rate when predicting vulnerabilities. And attack surface, the way it's defined today, it's hard to measure. As Lord Kelvin rightly pointed out, if you cannot measure it, you cannot improve it. So in a nutshell, there exist security metrics today which reflect the developer's view, but it does not reflect what happens in the deployment environment. With our security metrics, it reflects what happens in the development environment, and we try to evaluate the impact of these system security techniques. As a simple example, if we look at, say, IE5 versus Office 2000, if you just look at the number of vulnerabilities in them, you would say IE5 has 3 times as many vulnerabilities as Office 2000. But if you look at the number of exploited vulnerabilities in the wild, you would see that both of them have an almost equal number of exploited vulnerabilities. So for the rest of this talk, I'm going to actually go on the current metrics and the limitations that they have. Then I'll propose the metrics from our paper, and then I'll go over the data analysis approach, followed by the actual data analysis. Then I'll go over the implications before finally concluding. So presently, one of the metrics that is used is the number of vulnerabilities to assess the risk. If you have more vulnerabilities in a system, more is the risk to the system. And then there is the concept of CVSS score that is assigned to vulnerabilities. So CVSS actually measures the impact on confidentiality, integrity, and availability. It has other vectors like access complexity, access vector, etc. And each of these scores are actually decided by security vendors. And then the concept of attack surface was introduced. Intuitively, it is the number of different ways in which an adversary can enter the system and cause damage. And the way it is defined today, you require access to source code. The problem is that the first two metrics, they either do not capture the likelihood of attacks or the severity. Or CVSS actually claims that it does capture severity, but as prior work shows, it does not do a good job at it. And attack surface, the way it is defined today, it's hard to measure because you need access to source code and understanding the source code properly. And in general, these metrics do not reflect security in the field intuitively because, for instance, CVSS base score is a mathematical formula that depends on the impact values and the exploitability values. And the impact value actually is decided ahead of time by a security vendor. So a bunch of these things are arbitrary. And users can actually modify the attack surface, for instance, by reconfiguring the services on their systems. So with our analysis, we propose metrics along 3 different directions. First is if or whether a vulnerability is exploited. And under this, we have the exploitation ratio and count of vulnerabilities exploited in the wild as metrics. Then we discuss how often are products attacked, and we have exercised attack surface and attack volume as our metrics. And then we try to analyze when are attacks against these vulnerabilities seen. All of these metrics are based on field data, that is, they're computed on real hosts, and they are either computed on a per product or per host basis. For instance, the if or whether a vulnerability exploited metrics are on per product basis, whereas exercised attack surface and attack volume are computed on a per host basis. For the purposes of our analysis, we used the National Vulnerability Database. From this database, we actually used two fields. One is the CVE that is exploited and the vulnerable software list corresponding to the CVE. Then we use semantic attack signatures. Semantic maintains a list of IPS signatures and antivirus signatures, and it actually maps these signatures to the vulnerability it exploits. And these signatures are actually obtained by screen scraping the semantic websites. And then we have the Worldwide Intelligence Network Environment, WINE, which is another database maintained by Semantic. From this database, we use two datasets. One is the IPS telemetry dataset, which maintains a record of all the attacks that have happened on real hosts. From this dataset, we use the machine ID field, the attack time, or when the attack happened, and the corresponding signature that was used to attack. And then we use the binary reputation dataset, which actually contains information about all the binaries that are stored on a host. Our analysis consists of around 300 million IPS entries, over 6 million hosts from 2009 to 2014. And for our analysis, since we only look at the IPS telemetry dataset, we only consider network-based attacks. I would like to explain how we arrive at our metrics using the data we have, using an example. From NVD, suppose you have a product A, which has 10 different vulnerabilities. For the sake of this example, let's say it's CVE1 to CVE10. And then we have a product B, which has, say, vulnerabilities from CVE11 to CVE15. From semantic signatures, we would have information of the following form. Subsignature A affects CVE2. What this means is that for CVE2, there is a signature which attacks it, and hence CVE2 has been exploited in the wild. So if we combine the information from NVD and semantic, what we would get, for instance, is that from CVE1 to CVE10, you can see CVEs 2, 3, and 8 are exploited, and hence, say, for product A, there are 3 exploited vulnerabilities. And this is actually 3 out of 10 vulnerabilities that were disclosed, and hence the exploitation ratio is 0.3. And similarly, we can compute these metrics for product B. So with WINE, we also have information on what attacks happened on each of the machines. For instance, from IPS telemetry dataset, we have information of the following form. With machine 1, on 12 January 2014, for instance, there was an attack that was related to signature A. Recall that signature A actually affected CVE2 in product A. With WINE binary reputation, you have information of the following form. Product A was installed in machine 1 on the 1st of January 2014, which means the product existed at that time when the attack happened. So if we combine this information with what we had earlier, we would have information of the following form. In machine 1 on 12 January 2014, when product A actually existed, there was an attack on CVE2, which correspond using a signature A. And using this information, we can compute the exercised attack surface and attack volume. How do we actually do that? I'll come to it a little later. For the purposes of our analysis, we analyzed Microsoft Windows, XP Vista, Windows 7, and the corresponding service packs. We analyzed Microsoft Office 2000, 2003, 2007, 2010, Internet Explorer versions 5 to 8, and Adobe Reader versions 5 to 11. These are some of the popular products that are used, and hence we thought they're good candidates for our analysis. So now that we have discussed the proposed metrics and the data analysis approach, let's move on to the actual analysis. So the first kind of analysis we do is if or whether a vulnerability is exploited. For this, we have two metrics, as I mentioned earlier. We have the exploitation ratio and count of vulnerabilities exploited in the wild. What we define exploitation ratio as the ratio of the number of exploited vulnerabilities to the number of disclosed vulnerabilities. let me tell you that exploited vulnerabilities over here does not mean proof of concept exploits, but it actually means exploits that have actually happened in the wild. And we get this information from the semantic attack signatures. And both of these are per product metrics. And just to recall from the example that we took earlier, if product A has 10 vulnerabilities, out of which 3 of them are exploited, then the exploitation ratio would be 0.3, and the number of exploited vulnerabilities is 3. So one question that often comes up when you think of exploitation ratio is that there is some bias towards newer products. You may say cyber attackers have probably had lesser time to attack newer products. So we try to, in order to check if that is the case, we try to perform the following analysis. We try to see whether newer products actually have a bias. So using semantic signatures, OSVDB and WINE, using the first exploit date in each of these, we try to figure out when the attack actually happens after disclosure. And we realized that around 90% of vulnerabilities are attacked within 94 days after disclosure. And this result was also confirmed in many of these papers, including the recent Microsoft Security Intelligence report that was released, which said most of the vulnerabilities are actually exploited within 30 days after disclosure. So moving on to our analysis, first we try to see how exploitation ratio varies in between different products. First, we observe that the number of vulnerabilities actually exploited are really low, around 15% for the products that we considered. And the exploitation ratio actually varies in between different products. For example, if you look at Adobe Reader and Microsoft Office, you would see that Adobe Reader has a much lower exploitation ratio than Microsoft Office. And if you look at IE5 and Office 2000, you would realize that both of them have the number of exploited vulnerabilities to be the same, but the exploitation ratios of one is thrice that of IE5. And this clearly demonstrates the pitfall of using the number of vulnerabilities as a security measure. Another observation that we have is newer versions actually have fewer exploited vulnerabilities. For instance, if you compare Adobe Reader 10 and 11 with Adobe Reader 8 and 9, you would clearly see that there is a decrease in the exploitation ratio and the number of exploited vulnerabilities. And similarly with Windows Vista and Windows 7, you would see that there is a decrease in comparison to Windows XP. And we believe that is because of the newer security technologies that have been introduced. For instance, in ASLR and DP was introduced in Microsoft Vista, Windows Vista, whereas sandboxing was introduced in Adobe Reader 10. Well, another reason that is possible over here is commoditization of exploits that has been happening in the recent past, wherein if you have an exploit for one vulnerability, more hosts are attacked corresponding to that vulnerability. And this is another view of when we just look at operating systems. Over here we consider all Windows operating systems, and we compare the disclosed vulnerabilities with the exploited vulnerabilities. You see, when you look at the graph to your left, you would realize that the number of disclosed vulnerabilities has increased. However, if you just look at the exploited vulnerabilities, you would realize that it has decreased in the recent past. So you may argue, if you just look at the disclosed vulnerabilities, you would say the security has not improved, but if you actually look at the exploited vulnerabilities, you would say that security probably, newer systems are probably more secure. Moving on to the second part of our analysis, how often are vulnerabilities exploited? For this, we have two metrics, the excised attack surface and the attack volume. We define the excised attack surface as the number of distinct vulnerabilities that are exploited on a host in a given month, and the attack volume as the number of attacks experienced by a host in a given month. Both of these are per host metrics, and they are computed in a given month on a host. And just for the sake of an example, let's say in this particular example, all the entries correspond to one particular machine, and all of the entries correspond to Jan 2014. So we see that machine 1 on Jan 2014 was attacked by signature A, which is actually an attack on CVE2, and this corresponds to product A on machine 1. Using this information, if you try to compute the number of distinct vulnerabilities that are exploited in Jan 2014 on machine 1, you would realize that these This corresponds to vulnerabilities CV2, 3, 8, and 12. And hence, the exercised attack surface for this machine in Jan 2014 is 4. Whereas the attack volume, that is the sheer number of attacks that happen, is 6. In general, if you want to compute these metrics for products, you may want to average it over all machines that are using these products and also across all months that these machines are using these products. So moving on to the analysis, so on the y-axis over here, what we have is the average exercised attack surface, that is average over all machines and over all months. And the attack surface that you have in this graph only corresponds to the operating system vulnerabilities. One interesting observation is that with major versions of operating systems, we see a clear decrease in the exercised attack surface. And we believe this is because of newer security technologies that were introduced in Windows Vista and Windows 7, that is ASLR and DEP. If you look at the products, again you see a clear decrease, at least in IE and in Reader. And again, we believe this is because of protected mode that was introduced in IE7 and Adobe Reader 10. Another interesting observation is that if you look at the number of exploited vulnerabilities in IE and Reader, you would realize that Reader has fewer exploited vulnerabilities than IE. But if you look at the exercised attack surface, you would realize that Reader, except for maybe Reader 10, has a higher attack surface than IE. What this tells us is that Reader is probably easier for cybercriminals to exploit than IE is. Let us see how exercised attack surface varies over time. In this graph, the red curve corresponds to the total exercised attack surface on the hosts. The dotted blue line corresponds to the exercised attack surface contributed by the operating system, whereas the green line corresponds to the exercised attack surface contributed by the applications. First interesting observation is that apps contribute more to the attack surface than the operating system. Another interesting observation is that you see these 2 or 3 spikes over here, and all of these spikes actually correspond to one vulnerability, which is CV 2009-4324. This is actually an Adobe Reader vulnerability, and this tells us that actually even a single vulnerability can have a disproportionate number of attacks, and that can skew the system. So in this graph, we are trying to see how the exercised attack surface varies over hosts using different operating systems. For instance, if you look at, say, Windows 7 SP1, you will see that the exercised attack surface varies from 0.0 to 0.02. One question that you may ask is, since it varies a lot, can we actually reduce the attack surface? So in order to check this, we analyzed operating system vulnerabilities with most attacks, and we realized that amongst the top 10 operating system vulnerabilities, you could actually disable services corresponding to 6 of them. For the other 4, we realized that they could not be disabled because one of the reasons was maybe vulnerabilities. If there are vulnerabilities in files that are in kernel systems, you cannot disable them. So let us move on to the third part of our analysis, which has got to do with when vulnerabilities are exploited. The first question we ask over here is, how long do machines survive? What do we mean by survival? Survival means that a machine is not attacked for a vulnerability of an installed product. And we compute the survival probability using the Kaplan-Meier estimator. So in general, for our analysis, it may so happen that a host actually leaves a study without being attacked, and hence we have some sort of right-censored data, and actually Kaplan-Meier estimator actually takes care of it. The graph you see over here is the survival probability of Windows operating system. The first interesting observation is that with Windows XP SP3, the survival probability drops along a linear curve. But for other operating systems like Windows 7 and Windows Vista, the survival probability is quite high. The graph to the right corresponds to the survival probability of Adobe Reader. An interesting observation is that, for instance, for Reader 9, if the survival probability at the end of around 40 months, is around 0.4. What this means is that if you had Adobe Reader 9 installed on your system for around 3 years, there is more than half a chance that your system was attacked. And this is actually in comparison to the lowest value that you see at the end of 50 months in Windows is 0.96 or 96% survival. Another interesting observation is that with Reader 10 and Reader 11, the survival probability is quite high. And again, we believe this is because of protected mode introduced in Adobe Reader 10. If you look at the survival of IE vulnerabilities, you see that with IE6, there is a decent drop. But with i7 and above, it's much better. But in any case, i6, it's still 94% in comparison to 40% that we saw with Adobe Reader 9. And we believe that for i7 and above, it's better because of protected mode introduced in these systems, in i7. So let us move on to the second part of the time effect. We try to analyze whether upgrades of products actually have an effect on the accessed attack surface. What do you mean by an upgrade lag here? Suppose you have a product and you have version 1 installed, and the company releases, say, version 2 in the year 2000, and you decide to upgrade to version 2 in, say, 2001. In that case, we would say your upgrade lag is 1 year. And suppose version 3 is released in 2004 and you decide to upgrade to version 3 in 2007. In that case, from 2004 to 2007, you've been using an older product. And then we say, for this product on your machine, your upgrade lag is 3 years. And suppose the company again releases version 4 in 2008, you decide to not upgrade. And then again version 5 in 2012. And then you decide to upgrade to version 5 in, say, 2013. In this case, from 2008 to 2013, you've been using an old product, and hence the upgrade lag for your machine for this product is 5 years. So in general, product upgrade lag is how long a user continues to use the product after a new version is released. And when there are different versions involved, we consider the maximum upgrade lag over all versions of the product. So does the length of the time to upgrade have an effect on the attack surface? Turns out it does. The graph over here you see is the cumulative average attack surface versus the time for upgrade. The big curve that we see corresponds to Adobe Reader. The interesting observation here is that when the time to upgrade is less than 1,000 days, it is correlated with a low average accessed attack surface. So if you're the administrator of an organization and you have Adobe Reader, for instance, you would say, I would want to upgrade my systems as fast as possible. Since we cannot see IE and Office over here, let us zoom into those. And again, over here, we see that for IE, when the time for upgrade is less than 1,000, it is actually correlated to a low average accessed attack surface. So let us move on to the question that we first asked. Can we actually measure the impact of any of the system security techniques? And through our analysis in different ways, we've observed that our metrics actually show an improvement after sandboxing or protected mode was introduced in Adobe Reader 10 and Internet Explorer 7. And with Windows Vista, security was a major goal. And our metrics actually show an improvement in Windows Vista and Windows 7 after ASLR, DEP, and user account control were actually introduced. We cannot separate how each of these technologies actually had an effect, but we know that all of these together have had an impact. So what are the implications of what we discussed? One, we saw that there was a low exploitation ratio for newer products. Anecdotal evidence shows that cyber criminals are actually feeling scarcity of exploits. For instance, the author of the Black Hole Exploit Kit has allocated a budget of around $1 lakh for purchasing zero-day exploits. And there are actually exploit kits being rented or sold in the market. Our analysis shows that attack surface actually varies in between different hosts, and it actually takes into account user behavior, for instance, upgrade lag. And this can actually help in defining policies in enterprises. And as I mentioned earlier, certain security technologies have actually helped improve the security. So finally, a few conclusions. We observed that few vulnerabilities are exploited in the wild. The number of vulnerabilities actually do not correspond to the number of exploited vulnerabilities for products. The average exercise surface for Windows IE and Reader decreases with newer versions. Few vulnerabilities can have a disproportionate number of attacks. Users using Reader are attacked more in comparison to Windows and IE. And quicker upgrades correspond to reduced attack surface. Thank you, and I'm happy to take questions.
Questions? There is one down there.
Thanks, nice talk. Did you focus on very specific types of vulnerabilities, or did you just focus on any vulnerability you could find to one project?
As in, we considered all vulnerabilities, but for attacks, we only considered network-based attacks.
Okay, but it did not just filter on something that gives you remote code execution. You also looked at like denial of service attacks, information leakage attacks, all these kind of...
So we considered all vulnerabilities that were there in NVD.
Okay, thanks.
Actually, you're first. Always the same thing. Go ahead.
We don't like comment anyway. So, when you were talking about the exploitation ratio, it seemed like you're saying a lower ratio is better, but if you have the same number of vulnerabilities and a lower exploitation ratio, does that mean you're worse because people just aren't exploiting things? But they're exploiting just as much as the other software. They're just more that they could do. So
if they're not exploiting things, isn't it better?
But so if you had two different systems, both of them had 27 vulnerabilities that have been exploited. One had a lower ratio. That means that the lower ratio has more vulnerabilities total. They're just not exploiting. They're exploiting just as much as the other system. So how does that make it better?
Well, that was actually in comparison to the number of vulnerabilities. So presently, when you look at it, you say if one product has more vulnerabilities, it has a higher risk. But if you actually look at the number of exploited vulnerabilities, which we feel is better, you would realize that although one has more vulnerabilities, the number of exploited vulnerabilities is still the same.
Okay, so you're saying they're equivalent at that point.
Yeah.
Gotcha, thanks.
I have a question really fast.
Sure.
There are two things that I don't fully understand. First of all, it looks like you are taking sort of a snapshot at a certain point in time of the actual number of vulnerabilities for a certain piece of software. But in actuality, what happens is that during time, new CVEs are disclosed, and so there is a continuous variance or increase in the actual surface. So can you factor that in? Did you factor that in?
Actually, the CVs that we consider are right from the beginning. It's not for that duration. But the attacks we consider is, yes, a certain snapshot in time from 2009 to early 2014.
Exactly, so, but if an attack happens at times t, you're comparing that attack at that time with respect to all the CVEs that being disclosed through the history of that product. While it could be that attack arrived when only 3 CVEs were disclosed, right? And then at that point, the effect would be different.
Right.
It would be one exploitation out of 10, would be one exploitation over the 3 that were disclosed.
I think what you're saying actually is an important thing to consider, but actually that is not what we do over here. We only consider it at, say, from 2009 to 2014, we try to see what has actually happened. What you say actually has a lot of value in it, but I think what we do is something different, and it has value too.
Okay.
Interesting thought, first of all. My question is, have you looked at how bursty exploitation is? And by that I mean, is it fairly constant exploitation throughout that period, or is it the case that it is not exploited for a long period of time, and all of a sudden there's a campaign and you see a spike in exploitation?
So I think with one of the slides I showed you, when we saw how exercise attack surface varies over time, we actually saw a lot of spikes. And it's actually very bursty. So at some point in time, you would see a large number of attacks happening and then it falling down.
And was that because of patching, or
so patching is
still during the unpatched period?
So patching is actually an interesting direction which we did not consider here, and that is something that we would like to look at later at some point in time. But yeah, we do not know how patching has affected this analysis.
Thank you.
Other question down there?
Yes. Within the scope of Microsoft Office Docs detection, in recent years, they upgraded both their reader as it allows you only to view the files, okay, without editing, so it reduced the vulnerabilities. And also, they have also done disabling macros. So within your work, have you seen any other popular attacks within Docs that other than Microsoft Office of Macro?
I'm sorry, can you please rephrase your question?
Okay, I'll return. Are there any other attacks within Microsoft Office that are different from macro, like VBA?
Actually, we did not look at specific types of attacks happening. We looked at it from a quantitative perspective.
I see. Okay,
So
thank
the
you.
answer is he hasn't looked into that.
Yeah.
Mark? Oh, yeah. Yes.
If you ask analysts, security analysts at Symantec, they will tell you that macro viruses are very uncommon nowadays. So chances are that we've mostly looked at the ones that are not macro.
So I had just a clarification and then a question. So the clarification is you said you look only at, when you say you look only at network-based attack, what you actually mean is you only look at attacks for which a signature can be created so that the attack is detectable from the network point of view, right? But it can be, it's not a network-based attack as against a server or something. It can be a PDF document that
Yes.
contains something.
Basically,
So if that is clear, so how many of the vulnerabilities do you think could be exploited, for instance, like a polymorphic JavaScript or something like that, for which there is no IPS signature? So what is the coverage of the IPS signature versus the CVEs that you have looked at? Or I guess you have no precise idea of that, but can you give us an order of a magnitude?
Actually, I do not.
Okay, so that might be an interesting follow-up work.
Sorry? But for the wine analysis, we did not. We just looked at network-based attacks, right? Okay.
So yeah, I was hoping you could have said something about the host-based detection, but because I know it's also available. But anyway, so my question was about the average exercise attack surface. You had pictures, graphs, and there was this very weird spike for Windows 7 for which Windows 7 SP1 suddenly had much more value, even though you had a nice arrow going down. So can you just give us some hints on why this is so?
Let me just move on to that.
Yeah,
this one?
Windows 7 and Windows 7 SP1.
So the reason we believe that this happens is because with major revisions, the code significantly changes and they introduce newer security technologies. But the spike in between the same version, we believe, is because the code has been existing for a longer duration, and hence attackers have had a longer time to actually work on the same code. And that is why we believe, for instance, from Windows 7 to Windows 7 SP1, there is an increase. And it would be an interesting thing to check maybe 2 years from now how this behaves.
All right, let's thank the speaker.